University of Michigan. He's going to tell us about tunneling into microstate geometries.
Yeah, so, right, I'm Dan. Thanks for having me here. I really appreciate it. And yes, I'm going to talk about tunneling into microstate geometries. So this is just to sort of tell you what the sort of big questions are here. The big question here is about the black hole information paradox, basically. And I guess it's interesting because there's a lot of recent new activity there. I hasten to say that this has nothing to do really with the recent either Hawking, Perry-Strominger, or Toft's ideas. This is more older ideas that go back to Mathur. So this is related to the fuzzball program, Microstate program. That's where it's kind of situated. But I'll tell you more details about this. The important thing to understand is that what I'm going to be talking about is an old problem, really. And I'm going to say some general words about it in the first part. So it's sort of an introduction to what's the problem, and how can we look at this? Where do we expect this problem to be solved, maybe? And then in the second part, I'm going to explain our specific computation that we did to try to address this problem. Okay. So black holes, right? Black holes and their entropy have been a long-standing problem of gravity. As soon as Bekenstein and Hawking calculated the entropy of a black hole, there was a question, well, where does this entropy come from, right? If you have an entropy, you expect to have microstates that correspond to e to the entropy number of states, right, in a sort of statistical mechanical way. And the first example that we really found evidence that this has to be the case is in string theory, of course, the famous Strominger-Vafa paper, where they were able to look at a specific black hole, the D1D5P 3-charge black hole, and they didn't really, so what they did was not really counting the black hole microstates itself, right, because they were able to look at the same system at different string coupling, so they tuned the string coupling all the way down, and then we're able to look at this brane picture at 0 string coupling, and then count the microstates, right, the sort of excitations of this brane picture. And then, very crucially, you need to have the fact that these states are going to be, you have non-renormalization theorems about these states, and thus the counting of states in 0 coupling or the counting of states in the black hole regime should be the same, right? So this was sort of the success of Strominger-Vafa. More recently, so first with Luna and Mathur, the supertubes, and even more recently the superstrata, there's a program of constructing these solutions directly in supergravity. So instead of dialing the string coupling back and looking at a brane picture, the idea here is really to look at these solutions directly in supergravity, so at large string coupling in the supergravity regime. And there, this is basically the program of Josef Bena, Nick Warner, and many others. They've been able to construct fairly general solutions which they expect to correspond to microstates of this D1D5P, this 3-charge black hole. Yeah?
Do you need large Tiff's coupling? Because if the string coupling is large, why would I supergravity?
Right, sure, right, okay. I mean, yeah, I'd be very cavalier with my words here, being an introduction. Right, so this program here with constructing microstates is really constructing them directly in supergravity. And just a few words that I will repeat, but the point of a black hole microstate is that you have a horizonless, smooth geometry to take the place of the black hole. So it has to be horizonless, because if it has a horizon, then it has an entropy, and then it's kind of defeating the purpose of finding the microstates, right? Because then it should have its own microstates. So it's horizonless, but it's also smooth. So you could also construct, of course, supergravity solutions which have the same charges as the black hole, but which have singularities. But there, I would say you're not really finding a solution in supergravity, right? Because you have a singularity there in the metric, and then you expect that stringy effects, quantum effects would come into play and not really be described by supergravity anymore. So what they're really doing is they're constructing states in supergravity with only the supergravity fields, and they're smooth in supergravity. So why is this working is one of the questions that you could ask. Because it's not really a priori obvious that there are going to be enough microstates that you can construct in this way, right? And this is still actually an open problem. So for the Luna and Mathur supertubes, these are the microstates of the D1D5 or 2-charge black hole. You can pretty much see that there is a significant fraction, at least, of the entropy that is carried by these smooth supergravity solutions. But for the 3-charge case, it's not at all obvious that the superstrata, which is the 3-charge generalization of the supertubes, is going to carry enough entropy that you can construct enough of these in supergravity. And that's entirely reasonable, right? Because it's totally possible that you can have a general microstate not having a smooth classical supergravity limit, right? It might be inherently stringy or inherently quantum. So that's just something I wanted to point out, that this microstate program is not really definitely going to succeed in that sense. Yep.
Are you going to comment on, there was a recent paper by Martinick and Warner.
Mm-hmm.
Does that help with this problem at all?
So let's see, there's Martinick and Warner, that's very recent, right?
Yeah.
I don't think I've read that one. But I know Martinick, yeah, Martinick and Niehoff, and before that, Martinick alone, he's talking about like these W brains that wrap the
Right.
cycles.
Right, yeah.
So that could help in a specific sector,
Okay.
and I'd be very willing to talk about that because I think it's very interesting. But it's still not clear that will completely help as well. Yeah, and feel free to interrupt me and ask questions and all that. I'm going to gloss over some things, and if you ask me questions about it, I might go into more detail, or I might say I can't go into more detail without going over time. Good. So one question is, are there enough microstates in supergravity? Another question is, are these microstates that you can construct typical enough? Are they, enough like the typical microstate of a black hole to tell you anything meaningful about the physics? That's also a very interesting question. There are some arguments to say that these supergravity microstates are typical enough, but I would say that this is also largely unresolved. And then, of course, all of this that I've told you of so far is all supersymmetric. So this is only stuff that you can really do when you have a lot of control over your system, which means supersymmetry. And there's very little that you can do with when you throw that away. So for non-extremal black holes, microstates of non-extremal black holes, one way you can go is you can try to construct non-extremal microstate solutions, so non-extremal smooth solutions in supergravity. This is very difficult. The prototype example is the JMART solution. Typically, these solutions have some kind of problem, like the JMART solution. You don't have to be familiar with it. I'm not going to use it, but it's like overspinning, so it doesn't really correspond to any physical black hole that you would expect. Another line of thought is to take a supersymmetric background and introduce in the probe approximation. So you introduce a probe that's non-extremal, so that breaks supersymmetry. And then, of course, you can move a little bit away from extremality, from supersymmetry, but not, of course, a lot. And this is the line that Josef and Andrea and Bert did a bit. Of course, this still doesn't really answer a lot of questions that you might have about the non-extremal setting. And in particular, things like Hawking radiation are very difficult to study if you don't have a very good handle on non-extremal microstates, because you don't have Hawking radiation in supersymmetry if you have supersymmetric microstates. And in general, time evolution. And one thing that I'm going to focus on now is the formation of black holes. This is also something that you can't really study unless you have non-extremality. And the reason for that is essentially that if you really do have supersymmetry, then there's no real evolution, right? There's no physical process that can construct a supersymmetric black hole. You always have to look at supersymmetric black holes as a kind of limiting process, but can never really be constructed by a physical process. So, and in particular, there's no dynamics between different supersymmetric states. So if I give you a supersymmetric black hole, it's going to stay that way. If I give you a microstate, it's going to stay that way. You're not going to see any kind of interesting dynamics going on. So one way you could try to look at this is to go near extremal and to introduce probes in a supersymmetric background. In a sense, that's what we're going to do. But what you can also do is try to look at black holes in full generality and try to make some general arguments about that. And that's what I'm going to talk about now for a few slides. So let's now think about a fully non-extremal black hole.
Excuse me, why
yes.
do you need dynamics exactly to compute, let's say, entropy or something?
Oh, okay, yes, very good. Yes, thank you for asking, because I didn't really tell you why I'm interested in dynamics. So what I'm going to be focusing on is formation of black holes, and in particular, I could give you a black hole state, and I can give you all these fuzzball states, these microstate states. And now the question I want to ask is, when I have a collapsing shell of matter, what's going to happen, right? Am I going to form the black hole? Am I going to form the microstate? Some kind of superposition? And how do I determine this?
I see. So entropy is not your main concern.
Right. Entropy is not my main concern.
Information paradox or things like that.
Right. I mean, this is related. It's all very much related, right? Because if you have all these microstates instead of the black hole, then the information paradox is more or less solved. But yes. So my main concern here is going to be the classic infalling shell of matter, and then I'm going to say what's going to happen here. Yes, thank you very much. Good. So in full generality, non-extremal dynamics is obviously difficult to study. The only things that have really been said about these have led to a lot of confusion typically, so I just want to highlight the firewall debate. I'm not saying that everything that they're saying is wrong, but definitely there's a lot of confusion. I think we can all agree on that. And so in particular for formation, where's the problem? Okay, the problem is here. The classical intuition is very simple. You have an infalling shell of matter, and at some point, this infalling shell of matter passes its horizon radius, right? And at that point, you say there is a horizon. The black hole has formed its horizon. And this happens well before the shell reaches a singularity, and thus well before you get high curvatures, and you expect stringy quantum effects to take over and render GR not accurate. So what's going wrong? Because if I'm telling you that we have all these, I have all these microstates, but which get rid of the horizon, but I'm telling you also that if I take an infalling shell of matter, it should form a horizon, then what gives? And the reason that the classical picture is actually not accurate anymore is because there's a large phase space when this shell becomes horizon size. So let's back up a minute and look at a very simple quantum mechanics problem, just to give you a sort of a flavor of what I'm talking about. So this is a very simple example where you have a particle in a well. So we all know that if you have a particle with a barrier in one dimension, you have the barrier is not infinitely long and infinitely wide or whatever. You can have a little bit of the particle's wave function leaking out, right? This is quantum tunneling. This is always going to be an exponentially small effect. So after a time t of the particle sitting in the well, you can still approximate the wave function, the norm of the wave function that's sitting in the well still, which is this, in one dimension still. So the norm of the wave function still in the well is going to be almost 1, right? If epsilon is a very small number, then this is just going to be a very close to a number very close to 1. But now the question is, what happens when I have not one dimension but d dimensions for the particle to leak out? So in this case, the leaking out probability, let's say, the tunneling probability to leak out in any given dimension, in any given direction, is going to be the same, so it's just going to be this guy. But now I have to take this times d, right? So I take d copies of this one-dimensional wave function to get my d-dimensional wave function. And then I see that my probability for staying inside the well is now going to be e to the minus d times epsilon t. And now we see that if we take the number of dimensions to be very large, so larger than 1 over epsilon, the decay is almost instantaneous, and there's almost nothing left inside the well, right? So this becomes a very small number, and then the wave function of the particle has basically gone outside of the well. Even though that classically it's confined to this well, because it has so many different directions that it can tunnel out of, it instantaneously tunnels out of the well. And this is very similar to what we expect happens with a black hole. Okay, at horizon scale, you have a collection of microstates, fuzzballs, right? These are black hole microstates, and there's a very large number of these states. There's e to the s number of these, right? Because you expect that many microstates of the black hole to be. And if you take any one of these states, the probability of tunneling into any one of these states is going to be very small. So you can kind of estimate, this is sort of hand waving, you're saying that estimating the average curvature of one of these states is going to be about, or proportional to, let's say, the curvature of the black hole itself. And in that way, you can get that the tunneling probability to one of these states is going to be exponentially small with the exponent given by some proportionality factor alpha times the entropy of the black hole. And then you see that, well, look, my total tunneling amplitude is simply, this tunneling amplitude for 1 times n. And if my alpha here is around 1, in particular smaller or equals to 1, then my total tunneling amplitude will be of order 1, which means that it will instantaneously tunnel into one of these microstates, one of these fuzz balls. So what I want you to take away from this is that if there's a really large number of these microstates, then as soon as we get to horizon scale, which is when this phase space is accessible, as soon as we get to that scales, then if we have a sufficient cancellation of exponents, because that's basically what's happening, and this exponent is being canceled by this exponent, then we can have fast tunneling, and we don't expect a horizon ever to form, right? Because all of the wave function has basically been tunneled into the microstate collection. So this was arguments, these are arguments by Mathur from a few years ago, and then Krause and Mathur gave another argument last year where they tried to calculate this exponent alpha here. They considered Hawking radiation with back reaction and then extrapolated this result, and they said that, look, this kind of naturally gives you alpha equals to 1. So I think that's a very nice first step, a very nice kind of piece of evidence, let's say, but I won't say it's a complete proof that this is going to be true, because they didn't really do this from first principles. They didn't calculate this gamma I for each microstate.
In this discussion, what is the initial state that we're tunneling out of?
Right. So I've kept that a little bit fuzzy for some reasons, but let's say that my initial state is simply some state of collapsing matter.
Okay.
Yeah. Just at first.
Spherically symmetric? Yeah.
I mean, if it's totally spherically symmetric, that's probably going to give you problems with collapsing.
Mm-hmm.
Maybe it's also not completely possible to have something spherically symmetric.
So what do you assume for the initial?
We're not assuming anything, really. We're not assuming anything. We're just making some very broad and admittedly hand-waving arguments about very general, general things that we expect to happen.
So these degrees of freedom should be independent, yeah, because otherwise you can't say.
I'm sorry.
These degrees of freedom for tunneling should be independent of each other.
Yes, they should be completely different states. Is that what you mean?
Oh.
Or,
So is there an interaction between different?
well,
That could be very difficult.
yes. I mean, this is of course terribly difficult to make precise. I mean, because first of all, we don't even know the collection of microstates. We don't even know what the states are. So it's kind of not. I have no idea how to do this. But in general, I mean, I think this is no different than any typical quantum mechanics textbook program where you have a lot of states and then you can tunnel into, very much like the tunneling that I just explained in d dimensions of the particle. Or is that not looking there? So maybe
Starting with something that's close to a pure state, though, right?
sure, yeah.
I mean, something has to go horribly wrong when it's very far away from that. If this is hard.
Why do you say that?
Well, because if you take a really large star and it dies, it collapses and the horizon forms. And I don't see where this argument.
I mean, what I would say is that collapsing stuff seems to form a horizon from far away, but when you zoom in, it would really be in one of these microstates that doesn't have a horizon. So this is really the whole.
Well, I guess what I'm saying is, in that case, you have a macroscopic state that may have so many. I don't know how you count that then.
Right.
The entropy of that thing has to be able to have enough space to move out into these states. And you're looking at things where you have one or two or a handful going to this enormous number. But if you have an enormous number trying to get into a not quite enormous enough number, then this would fail and you would form a horizon, right?
Well, I mean, you're always starting from just one state. Now, even if it's a mixed state, there should be a proportionate number of states that you can tunnel into, of fuzzball states that you can tunnel
Right,
into.
well, you can set it up so that the problem is nowhere near quantum at the time that it's happening, right?
Well, that's the whole point. So I would say that at horizon scales, and that's what they're trying to say here is at horizon scales there is no such thing as beyond not quantum. There is no such thing as classical approximation. Even if you just take some spherically symmetric infalling shell of matter, at horizon scales it looks like there's no large curvatures, etc. That's what you're saying, right? like you can make it sort of look like classical should be fine. What they're saying is, look, there is no such thing as this because of the phase space, the large phase space that you can tunnel into. You really need to look at large effects at the horizon. There's large quantum effects at the horizon. And this is like this is definitely not a very concrete argument. I can't back this up with calculations, but this is sort of the idea of how you resolve the whole information paradox. Because if you have fuzzballs instead of black holes, then if you throw something in, it's smooth, so there's no singularity to hit, and it can come back out, with some information or not. Or
Sure, I'm just trying to untangle like what part of the assumption, for example, says that the state, the number, in some sense you have to have with such a system that's actually macroscopic, you should have a large, you may have one state, quantum state, but it may be highly entangled under various regular atomic level states, right? And then you need to encode that while you try to map to this high set of degrees of freedom. Your phase space may not be as large as it seems.
I'm not sure that's true. I mean, I think what I'm talking about is we can discuss this later more if you want, but I think the point is here that the collection of fuzzballs is really depends on what your like conditions are, of course, right? Like what do you know about the system? So if you have, this is very much thermodynamics versus statistical mechanics as well, right? So if you know only the mass and charge and angular momentum, stuff like what you would really usually know about a black hole, then I tell you there are e to the s states that correspond to this kind of a black hole. But of course, if you single out, one particular state with, these particular quantum entanglements, and then probably only have one fuzzball to tunnel to. But that's kind of a different question. Okay, more questions about this?
A very naive question. These microstates, they live on the horizon, along the horizon?
So I would say that the typical size of these states is about the horizon scale. This is, so if you look at these microstates from very far away, they look exactly like the black hole. They have the same asymptotic fall off, so the same charges, etc. But as soon as you zoom into around the horizon scale, this kind of order of magnitude, that's where they start to differ from the black hole geometry. All right, so I've said this, of course. These are, this is some rough estimates, some hand-waving arguments based on a lot of assumptions and extrapolation. Some particular questions that might come to mind, which we're going to focus on, is we've assumed here that all fuzzballs have pretty much the same kind of tunneling amplitude, right? We've just kind of approximated the tunneling amplitude into one fuzzball, but what we really want to do is we want to know for each individual fuzzball what the tunneling amplitude is. So you could ask, this will obviously depend, on the initial state, right? Different initial state will give you different amplitudes into different final states. That's kind of obvious. But there might be some intrinsic differences where you can say, this kind of microstate is always going to be more preferred to another microstate, or in general going to be more preferred. So our goal will be exactly to study this. So we're going to study this exponent in the tunneling amplitude to make a microstate. We're going to study in particular this assumption that it's fast enough, so that the tunneling happens fast enough to form microstates before the black hole horizon has a chance to form. And we're also going to focus on the fact if alpha is going to be the same for all microstates or not. And to do this, I must emphasize we're not going to look at all of the microstates for any given system. We're going to look at a very specific class of microstates, and we're going to calculate their tunneling rate. So in particular, we're not going to be able to say anything about this total tunneling amplitude. Remember, this was total tunneling amplitude, which would be of order 1 if the tunneling happens fast. So we're not going to be able to make any statements about this total tunneling amplitude, because to do that, you would have to know all of the states, and you have to know all of the tunneling amplitudes into all of the states. So we don't have that. Okay, good. So any questions before I move on to our specific setup? All right. So this may seem like a lot of slides, but it can go pretty quickly. I'm going to introduce now our specific setup where we're going to be working in. So in particular, we're going to be working in supergravity, right? We're looking at supergravity microstates. And these microstates you can look at from a 4D or 5D perspective, or 10 or 11D perspective. I'm going to give you some differing viewpoints, just so that any language that you're more familiar with, you can pay more attention to that. So these geometries are called sometimes the Neff multicenter geometries or the Bénard-Warner bubble multicenter geometries in respectively 4 or 5D. They are microstates of the 3 charged black holes. So if you want to think of 11D picture, the 3 M2 charges. Or you can also think of a D1, D5P frame. These are all kind of related, of course. How do these geometries look like? Well, these geometries are, so let's focus on the 5-dimensional picture. So forget about time, we have 4 spatial dimensions left. The 4 spatial dimensions are a flat R3 and a fiber over this R3. And this is the depiction of the R3, a line, and then this is the fiber in the R3. And as you see, there are multiple points in the R3 where the fiber, where this extra fiber shrinks to 0 size. Okay, and these are called centers in the language of Bénard-Warner typically. So these give rise to, of course, topologically non-trivial S2s, right? So between 2 of these centers, you get a topological S2 given by the fiber, and these are typically called the bubbles. So the reason why this gives you some interesting physics for black holes is because charge, of course, if you have 3 charges at infinity, this needs to be supported somehow on the interior. And the way that these geometries support it is basically by introducing flux, magnetic flux, on these non-trivial bubbles. So magnetic flux on these non-trivial bubbles is possible because of the non-trivial topology. And these fluxes then combined by, essentially by Chern-Simons terms, give you sort of sources for electric charges at infinity. So very importantly, these guys have the same charges at infinity as a 3-charge black hole, but they are smooth and horizonless. So these are exactly what we want for microstate geometries. So a few more things. As I said, there are any number of centers you can introduce in R3. These centers and the fluxes that you introduce on the bubbles here are not completely unrelated. You can't just choose them arbitrarily. They are related by what's called the bubble equations. And the only important thing I want to say about that is that certain configurations of centers and fluxes admit what's called a scaling solution, where there is a limit that you can take all the centers to coincide to each other. So you're given a number of fluxes, you distribute them in a certain way, and then you see that somehow I can configure my centers to take a limit to coincide outside of each other. I'm not going to say anything more about these scaling solutions other than that they are important for black hole physics, or expected to be the most important kind of solution within this class of solutions for black hole physics. Good, so just a little bit more about the 10D, 11D perspective, if that's maybe more familiar. So you can get this from a 10D perspective, let's say, if we just take, so these guys uplift to 10 dimensions, these centers then uplift to D6 branes. Of course, in 11 dimensions, this becomes KK monopoles, so that's how you see that smoothness coming in, because KK monopoles are smooth. The fluxes that I said are threading these S2s become D4 brane charges, D4 dipole charges, and you can also see this as a flux, a magnetic flux on the D6 brane in 10 dimensions. The electric charges then, that you can actually measure at infinity, so these are the physical charges, are given by the D2 brane charges, which come from essentially the F wedge F flux on the D6 branes. And I should also mention that there's D0 brane charge, or angular momentum in the 11-dimensional perspective, from the F wedge F on the D6 branes, just to give you the higher dimensional perspective of these guys. So you can also construct these as basically fluxed D6 branes, and that's the Neff picture. Good, so that's our background. Now in this background, we're going to introduce probes, and these probes are exactly going to be the things that we're going to be studying the tunneling of. So, as I said, we have these fibers here, and we can introduce a D4 brane wrapping this fiber, which is going to be a dipole because it wraps this contractible cycle, right? The cycle contracts here, so it's a dipole. And this D4 dipole can carry some extra charges, which are going to be D2 charges, which gives rise to a supertube. So a supertube, if this is not known to you, is basically just in this context, a D4 brane dipole with some D2 charges induced on it by magnetic flux. Now, what you might think is that this dipole here might want to shrink and pinch off here, but it's exactly the charges that prevents the D4 brane from doing that. So if there were no D2 brane charges on the D4 brane, then it would just want to contract and annihilate itself because it's a dipole. It's exactly these D2 brane charges that kind of form a repelling force that also give it angular momentum and repel the D4 brane from itself from collapsing on itself and stabilizing it at some finite radius. And that's exactly what you see here. So here it's been stabilized at a finite radius. So for these supertubes, for these branes, we can calculate the explicit potential in this background. And in particular, you can study the potential in this whole R3. So depending on where you put the supertube in the R3, so this, you see the projection here is just a point in R3, it can be supersymmetric or not. And one more important thing that I want to say is that I can by hand take this supertube and drag it onto one of these centers, thereby destroying the D4 brane dipole and in creating only branes. So this will be exactly our mechanism for creating new smooth centers. We're going to take some branes, put them on one of these centers, right? So I've just introduced some branes, and then to make something smooth out of that, I'm going to pull it over this cycle here so that it becomes something extended, becomes a supertube with an extra dipole charge, but it also becomes something smooth. So I want to just give you an example of a potential here. So if I just look at one dimension in the R3, I could, for example, take this R1 here to be this point here, and then this red point to be here. And then we see that there are really two supersymmetric minima here and here. And one of the supersymmetric minima is where the dipole is gone, where we don't have a supertube, we only have the D2 brane charges. And so what I can do is I can study having the charges here and then tunneling them to the other supersymmetric minimum here, where I have a supertube wrapping the fiber non-trivially. And that's exactly what we're going to be studying. We're going to be studying tunneling from one supersymmetric minimum, which consists of only branes, to a supersymmetric minimum where we have a supertube.
This is the potential of the probes?
Yes, this is the potential that the probe sees, exactly. So basically I've plotted here the energy of the probe in the background, depending on where it is. Okay. Good, okay, so I think I'll skip this actually. But what I want to, I'll pause a minute for questions. Is the background and the probe a little bit clear? So I realize that there are some details that might not be completely familiar if you haven't seen these systems. But sort of the big picture is we have these backgrounds. They have a different number of centers, which means also a different number of bubbles, topological bubbles. And we're going to try to make new centers by sort of pulling branes over one of these bubbles and creating supertubes. Okay, please ask me questions if this is clear. Right. So for this particular class, one obvious question is, how many bubbles do we prefer to have? So if I'm giving you a collection of branes to start with, and I let it collapse into a black hole microstate, do I get 2 bubbles out of there? Do I get 3 bubbles? Do I get 100 bubbles? 1,000 bubbles? Which number of bubbles is preferred? Which number of bubbles will give you the largest tunneling amplitude? So what we're going to do is we're going to calculate the explicit tunneling amplitude to form such an n-centered microstate with so many bubbles. And we're going to try to study the scaling of this exponent here with n. So this exponent beta, so the exponent beta in the exponent b, right? This is what we're going to be after. So, and again, disclaimer, this collection of states that we're looking at is not going to be enough even for the correct scaling of the 3-charged black hole entropy. So we're just looking at a very small. All right. So I've explained my background, my probes, and what we're trying to do. So now I want to tell you the dynamical process that we're going to be modeling. So one of the partial process, we're going to divide this process up into many steps, right? We're going to incrementally make a new bubble every step. So in particular, in an intermediate step, we're going to go from having n centers to adding a few branes and getting a new center out of it, right? From n centers to n plus 1. So our starting point for this is just to start from a background with n centers. And we're taking them for technical reasons on a line because it's much easier to write down the solution for this if all the centers are on a line. So we have our n center solution on a line, that's this here, right? So these are all just centers, and we can go on here as much as you want. This is my background solution. And then I bring in the new charges. So basically, you can either view this as a partial part of the collapse that's happening, right? So more branes coming in to form the black hole. Or you can sort of imagine yourself sitting at infinity, slowly throwing in branes part by part into the black hole microstate to slowly, do this process incrementally. So what I'm doing is I'm bringing in some new branes from infinity, and what I'm going to do is I'm going to do this by hand. So I'm going to take these branes and I'm going to, by hand, put them on top of the microstate, and in particular put them on top of the leftmost center here. So there's no cost to this because I'm allowing my angular momentum to change continuously. This is necessary, otherwise it can't move. And it's also something that I do by hand, right? So, because I'm adding angular momentum to the system. And then you can prove that this can happen completely adiabatically, completely smoothly without having to tunnel over it. And of course, I emphasize that we have to take a small amount of charge, because otherwise the bubble equations are not satisfied, and also because we're in probe approximation, so things would break down. Okay, so bring the charge over. Charge is now sitting over here. Of course, at infinity, we have a lot more charge left, but we're not going to care about that anymore at the moment, right? We're going to just incrementally do our process. So now we have a little bit of charge here. And now I'm going to do what I just told you earlier about the supertubes. I'm going to take these branes, and I'm going to pull them over the fiber between these two centers into a supertube. So a little more concretely, we have a old center, right? This old Kaluza-Klein monopole center, this old D6 brane, if you will, and I added some new charge to that, and I'm going to split this again into a new Kaluza-Klein center that's going to remain here, and a supertube that I'm going to pull over and make a new center here. And you might be worried about the fact that all of the centers here are Kaluza-Klein monopole centers, while the new one that I'm adding is a supertube, and not, strictly speaking, one of these D6 branes. But you can relate these by spectral flow, so it's not really something we should be worried about, probably. Okay, so this is where all of the magic happens in this step 2, because this is the tunneling, right? We have the charges on this center, and then we have a tunneling amplitude for them to tunnel into this new center, creating our new n+1 center solution.
Why is it okay for the D0 brane charge to vary continuously? Shouldn't it be quantum?
Okay, so one quick answer is because this is basically the only thing we can do technically. So you can kind of imagine having sort of a bath of angular momentum sitting around, or just, yeah, some kind of process in which you can add angular momentum as you wish. But I do agree that this is something that you add by hand, and it's not something that is intrinsically physical. Yeah. But this is mainly just technical. Yeah. I'll return to that at the end when I discuss some pitfalls here. Good. So to go from this one event, right, this incremental event, to the total process of creating the entire black hole microstate, we can do a simple calculation. So what we do first is we calculate this incremental process at different values of n, right? So at different, for different solutions. And then from this nice, from these different values of n, we can extrapolate the scaling behavior for all n. And this scaling behavior will look something like this. So the exponent here, the tunneling exponent, will always be linearly proportional to the probe charge. It will also be proportional to the background charge. This is not so important. This kind of follows from dimensional analysis. But it will also be proportional to a non-trivial factor of n. And it's exactly this factor of n which will give us something interesting. This is only the intermediate process. Now we say, okay, to form my entire black hole, which has n total centers and q total charge, I'm going to do this process n total times, right? I'm going to divide the process into n total incremental things. And each time I do this, this tunneling thing, I'm going to take a probe which has a charge of basically the same, right? So q total over n total. So I'm going to do this tunneling process n times, and it's going to be the same probe that I'm going to be tunneling. And in that case, all I have to do is really sum the intermediate probabilities to get the total tunneling amplitude. And this is going to be then proportional to some power of n total. And this is where we can get the physics out, right? Because when we have this exponent beta here, whether it's larger or smaller than 0 is going to tell us whether more centers are preferred or not. So in particular, if this exponent is smaller than 0, and we'll see that it is, it'll be faster to tunnel into more centers, right? Because as n gets larger, then this exponent will get smaller, and so the tunneling amplitude will get larger. So anyway, it's a bit confusing because of the minus signs and denominators, but the point is, if this beta exponent is going to be smaller than 0, then more centers will be preferred. It'll be faster to tunnel into more centers. And so our results are exactly this. So beta, we found, is smaller than 0. In particular, we looked at two families of microstates, one of them non-scaling and one of them scaling. And we found two slightly different. One is -1.5 and one is almost -1. Our exponents for beta. And I guess the important things that I want to show you about this is we looked at two specific classes, and we found that in both cases this beta exponent is smaller than 0. So our intuition is that probably this beta exponent will not become larger than 0 for any other kind of class, because we looked at pretty much, in these classes of scaling and non-scaling, these are pretty general solutions. But because they're not the same, we can also say that it's clearly not a universal property, right? This beta is not a universal property. So we're not really sure that for every given class of microstate, we're going to have a beta smaller than 0. That's definitely true. Okay, so let me immediately segue into saying some things about the pitfalls of what we just did. So what I just explained to you was that we were tunneling from a supersymmetric minimum to another supersymmetric minimum, right? We had brains sitting on top of a Kalu-Klein monopole, and then we tunneled them to be a supersymmetric supertube somewhere else. But I also told you in the beginning that if we have supersymmetry, there's no dynamics, right? Because states that are supersymmetric are not going to tunnel or decay into anything else. In which case, we should have found that gamma is equal to 0. And in principle, you should need an extra bit of energy that you add to go above supersymmetry to get a non-trivial tunneling amplitude. Now, this is entirely true, but let me again bring up this one-dimensional particle in quantum in a potential barrier. What happens when you expand the tunneling amplitude for this case in powers of the energy above 0 is that you see that it's linear in this energy, but the exponent does not depend on the energy. And that's exactly the point here. We're only really interested in this exponent and not the prefactor. We're really interested in this exponent because of the effects that I told you about in the introduction. So in this limit, where we're only interested in the exponent to leading order, it's perfectly fine to set the energy to 0 and do the calculation, even though we should have in the back of our minds that, well, if we really want to make any physical sense out of this, we have to introduce some non-supersymmetric energy needs. So that's one thing that I wanted to highlight. Let's skip this again. And right, so then about our results, you might say that, well, our beta is smaller than 0 should imply that it's faster to tunnel into more centers. And you might say, well, I'm only bounded by the quantization of fluxes on these centers, right? Because I want to make my number of centers as large as I possibly can, but of course, each one of these bubbles has to have some flux on it to keep it from collapsing. And so I'm kind of limited by putting one quanta of flux on each of these bubbles, and that's the number of bubbles I can make. So that would be sort of the initial thought that you might have when you see this kind of scaling with n. But as I said, The exact value of this beta depends on the details of the microstates, clearly, because we didn't find a universal value. So that I said already. What I haven't really said much about yet, or anything about yet, is that what we're looking at here are microstates of the maximally spinning black hole. Now that has to do with the fact that these are just, that all of the centers were on a line, and this gives you automatically sort of this maximally spinning black hole. And it's very difficult technically to go away from this assumption. So I should qualify our results by saying that we're really looking at this particular kind of black hole which has a lot of angular momentum. And it's not obvious how to generalize this to lower angular momentum, which also ties back into what we're doing with this adiabatically letting angular momentum differ. And again, we said nothing about the number of states available, and it could be possible that there are more states with small n. So in particular, there are certain arguments in the superstrata literature that suggest that 2 centers are almost enough to get all of the entropy for the black hole, or at least parametrically enough entropy, so the correct scaling of the charges. This might be true, and still be completely consistent with our findings. So all we're finding is that for a small number of centers, it might be more difficult to go into a particular state, but in the same spirit as for the black hole in total, it might be easier to go into states with small number of centers because there's so many of them compared to a large number of centers. And of course, all of this depends on how many ways that this extra excitation energy can be added to the microstate, right? Because the eventual final state of your system is going to depend a lot on what the initial state is, and in this case, it's going to depend a lot on how you go above supersymmetry, if that makes any sense. And then finally, one thing that I definitely didn't tell you about is the formation of the first bubble. So I told you that I'm adding charge from infinity and then pulling this charge over a bubble to create a new center, but if we don't have a bubble to pull stuff over, I can't do anything. So there's the problem of, let's say, the catalyst first bubble that has to be present in order for us to be able to do our procedure at all. And this is something that you can't really study, and I think this is a very, very interesting open problem. It has been for a while, how to get some non-trivial topology from just branes in a dynamical process. Okay, good. So let me just summarize and give you a little bit of a outlook as to what's left to do. What I've been studying was a specific class of microstates, and we studied the tunneling amplitude into this class of microstates, and in particular, its exponential behavior with the number of centers. We found that beta is smaller than 0, which means that more centers is preferred. What I want to point out is that this is really a first calculation where you could really look at the numbers, let's say, the first clear calculation of a tunneling amplitude for going, instead of going into a black hole, into microstates. However, it's very difficult to generalize this, and in particular, there's a number of pitfalls that we couldn't avoid. For example, we have to look at black holes of maximal angular momentum. We don't really know anything about how many states there are for a given number of bubbles, and that will be important for the total tunneling amplitude, right? And we can't say anything about the formation of the first bubble, which is necessary as a catalyst for our procedure. So in the future, it would be interesting to relax these restrictions, and of course make some kind of relation between the total tunneling amplitude and the entropy, because in the end, of course, when you sum up all of the tunneling amplitudes, you hope to find something a la Krauss-Matur, where the total tunneling amplitude is 1 or something like that, so that the tunneling happens fast and you never get the chance to form a black hole horizon. All right, so I'll stop there. Thanks.
Any questions for me? Can you put back the slide next week with the video? Sorry, there was some comment somewhere about the superstrata, and I just wanted to understand exactly what There.
So here.
Yeah.
So-
So, yeah, what does most small earth have to do with superstars?
Well, so the superstrata are basically two-centered solutions, supertube, substrata. And the arguments there would be that even if you only have two centers, you have enough entropy, or at least correct scaling of charges and all that in the entropy, so that you don't really need to consider the higher number of centers.
I see.
And in that sense, the higher n would just be sort of subleading effects. However, yeah, that could definitely be true. All we've said here is that it's if you have the same number of states, let's say, at small n and large n, then we definitely prefer large n. That's really the only kind of statement we can make about that. Right?
I see, but there's not, I mean, nobody really knows how to count the number of states beyond 2 centers.
Well, no, nobody definitely knows how to do that. Nobody also knows how to do that in a non-extremal case, because there are, so you can imagine moving the centers sort of in a slow way. You can also imagine sort of having the bubbles fluctuate in some way, and there's a lot of ways to add some energy to it. It's not clear how to calculate it.
Any other questions?
Does it make sense to try to, does this question make any sense? Do these superstrata and superfluxes or anything, do they have some, should we think of them as potentially giving a quantum sort of origin or soft hair? Does this process of pulling things, first of all, that process sounds a lot like these, the Borel effect, where you pull brain through and you get another brain and you get this.
You get a brain stretch.
Is that first of all similar?
No, I don't think so. That has more to do with sort of the interplay between, I would say, like the different D brains charged under each other, sort of, right?
Yeah. Well, aren't you taking a brain and pulling it over a bubble that is somehow
Yeah, I mean,
the configuration of the brain?
Yeah,
It sounded like at some point you were pulling like
but in a sense,
two P2s to D6s and stuff.
right. But in a sense, there's still like you can choose how much dipole charge you introduce to the system. So you pull brains out, and the number of brains obviously is going to be fixed, and by pulling this out, you introduce a new dipole charge, which is a supertube. But you can choose how much this dipole charge is. So I'm not sure what the relationship. About the soft hair, I think the point with the soft hair is that there's really sort of a memory effect, right? In that it's not really the initial or the final state that you're interested in, but really the transition between initial and final state.
Right.
And in particular, I would say that for these supersymmetric microstates, they're all kind of just they're stationary, so there's nothing going on here. So I
Well,
don't
instead
think.
of it being a sort of physical process where you keep creating them by pulling things
Yeah.
to other things.
Yeah. I mean, so it's obviously something that I don't really know, but my guess would be that it's probably not related, and if it is related, then maybe, as you say, somehow the creation process of doing this will introduce some kind of soft hair when you look at the full back reactive process, which we obviously can't do, then something will happen like that, and you can keep track of it. But I have no idea.
Other questions?